Good morning and welcome back. This section is section 5 of chapter 6. This is the beginning of the second half of the chapter. The first half we were working with just polynomials, adding, subtracting, multiplying, dividing, factoring. This section, this half of the chapter, at least the beginning part, we're going to be working with polynomial equations. We're going to be solving for them. So our answers are going to start looking like x equals something. We're going to be using the skills that we learned in the first half, specifically factoring, to help us do this. So, and this is one of the sections where it gets a bit meatier. It's a little bit tougher for part of it, but we'll see that when we get there. So, our learning targets today. I can identify the multiplicity of roots. This is really easy. All this is saying is how many times does that root happen? We'll see that in a second. The second one is I can solve polynomial equations by factoring. Now this would be factoring using special factors, factoring like a quadratic, factoring by grouping, factoring things out, and using another method that we're going to be looking at today. So to solve by factoring, using what we already know, and remember from chapter 5 with quadratics, if a times b equals 0, then a equals 0 or b equals 0. The marvelous thing about this is that it extends beautifully. If a times b times c times d times e equals 0, then something has to equal 0 in there. And so we're going to set everything equal to 0, and then we're going to factor it all out, so we get something times something times something times something equals 0, and then we can set each of those individual things equal to 0. Again, very similar to what we did last chapter with quadratics. So, let's look at one. X cubed plus 6x squared minus 5x equals 30. First thing we need to do is we need to set it equal to 0. Everything has to be equal to 0 when we're going to factor. That's simple enough. We just subtract 30. Now we need to factor this. If we think back, well, let's see, factor out what they have in common. Well, they don't all have anything in common because the x cubed is just x's and the 30 doesn't have any x's. Second step, look at the number of terms. I see 4 terms here, which says, can I factor by grouping? Well, if I took an x squared out of here, I'd end up with an x plus 6. If I took a negative 5 out of here, I'd end up with an x plus 6. So let's factor by grouping. So now we have x squared times x plus 6 minus 5 times x plus 6. We look at our 2 terms. Hey, this one has an x plus 6, and this one has an x plus 6. So let's take that out, and what we'll be left with is x squared minus 5. If x plus 6 times x squared minus 5 equals 0, well, we have something times something equals 0. X squared minus 5 isn't going to factor anymore because it's not something squared minus something squared. If that was x squared minus 4, we'd have x plus 2x minus 2. But x squared minus 5, we'd have to go x plus root 5, x minus root 5. We don't need to do that. We can solve this as it is because right now we have x plus 6 equals 0, or x squared minus 5 equals 0. If x plus 6 equals 0, that means that x equals negative 6. Easy enough, just subtraction. If x squared minus 5 equals 0, means x squared equals 5. Square root both sides to get x equals plus or minus the square root of 5. Remember, when we square root both sides, we need plus or minus. A number of people lost some really easy points on that last test by just not putting a plus or minus sign. And so we have our 3 roots. X equals negative 6, or positive root 5, or negative root 5. So that's one example of solving by factoring. We're going to go through a few examples here because there's just a lot of different ways that this can be presented. So we're going to see a few of them. Let's look at this one. We have 4x to the 5th minus 8x cubed plus 4x equals 0. Step 1 in factoring. Factor out what they have in common. Hey, they all have an x. Oh, and they all have a 4. So let's factor out a 4x, leaving us with x to the 4th minus 2x squared plus 1. Notice that 4x doesn't just go away. It sits on the outside. Well, x to the 4th minus 2x squared plus 1. Let's see. Second step, look at the number of terms. We have 3 terms. Can we factor it like a quadratic? Well, we have squared and 4th. This one is 2 times that one. So it's possible. Well, let's see. Can we think of 2 things that will multiply to give us 1 and add to give us negative 2? If you're thinking negative 1 and negative 1, you would be correct. So this is just x squared minus 1 and x squared minus 1. So from here, we can factor each of these because this is a difference of squares. So we get x minus 1, x plus 1. And this is also a difference of squares because it's the same thing. It's x minus 1 times x plus 1. Now we have a whole bunch of things multiplied together. We can see what could equal 0. First one, 4x could equal 0. Well, let's see, if 4x equals 0, either 4 equals 0 or x equals 0. 4 won't equal 0. 4 will equal 4. It's a constant. But x could equal 0. Second one, x minus 1 could equal 0. Then x plus 1 could equal 0. And then x minus 1, we already have an x minus 1. We don't have to put that there again. Same thing with the x plus 1. This is going to get into the multiplicity. Notice that these factors happen twice. That means each of those roots will happen twice. We don't need to solve each of them individually. We just need to recognize that it'll happen twice. So let's see, if 4x minus 1 equals 0, that means x equals, not 4x minus 1. If 4x equals 0, that means that x equals 0. If x minus 1 equals 0, we can add 1, get x equals 1. And x plus 1 equals 0, we can subtract 1, we get x equals negative 1. And so, x equals 0, 1, or negative 1. 1 and negative 1 have a multiplicity of 2 because it happened 2 times. If you're asked to state the multiplicity, you don't have to actually write out the word multiplicity. You can just put m2 next to them. It's multiplicity of 2. I'd say you could put times 2, like with the little x for times, except that could get confusing with our x's in the equations. Alright, so that was factoring, just like we've been doing. And then we had it equal to 0, and so we can solve it just like we did with quadratics. Something I want to point out here, notice in this first example, how many roots did we have? 1, and then positive root 5, negative root 5. We had 3 roots. Oh, look, it's x cubed. Weird. How about down here? Let's see, we had 1, 2, 3, 4, 5 roots. X to the 5th. That's strange. I wonder if that's a pattern that we are going to be looking at later on this week. Nah, it's probably nothing. So let's look at another example, though. X to the 4th minus 2x cubed minus 2x squared equals 0. First step, factor out what they have in common. They all have x's. In fact, they all have at least an x squared. And then you might think, oh, and 2's. No, that one doesn't have a 2. But they all have x squared in common, leaving us with x squared minus 2x minus 2. And so now we can look, how many terms do we have? 1, 2, 3. We have 3 terms in there, so we can factor it like a quadratic. In fact, that is a quadratic. Notice, x squared minus 2x minus 2. Well, alright, so what times what equals negative 2 and adds to give us negative 2? Not coming up with anything. But that's okay, because we have other ways of dealing with quadratics. In fact, a lot of times, when we have a polynomial, we're going to work on getting it down to a quadratic. Because once it's a quadratic, we can deal with that. If we can't factor it, we can quadratic formula it. And so that's what we'll do. But first, we have x squareds that could equal 0, in which case x will just equal 0. And notice that's a double root, because there's 2 of them there, x and x. And then for the x squared minus 2x minus 2, we use a quadratic formula. If you don't remember what that is, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We just need to plug in 1 for a, negative 2 for b, and negative 2 for c. So we do that. We get there. Notice I didn't plug in the 1s for the a's because it's all times 1. Doesn't matter. And so then we can square. Negative 2 squared is going to be 4. Negative 4 times negative 2 is going to be 8. So we have the 4 plus 8 there. 4 plus 8 is 12. And then 12 is 4 times 3, or 2 times 2 times 3. Those 2's can make a break for it. One of them makes it out. What happens to the other one? That sounds like a good comment thing. But one of them makes it out of their square root prison to get 2 plus or minus 2 root 3 over 2. And then just simplify the 2's. Remember, when you simplify the 2's, you have to simplify it from both pieces on the top. I actually recommend just splitting up the denominator. Go 2 over 2 plus or minus 2 root 3 over 2. It makes the simplification a lot easier, and chances are you won't make that common mistake. But when we simplify, 2 over 2 is 1, plus or minus 2 over 2 times root 3 is root 3. So we have 1 plus root 3, 1 minus root 3, and then 0 and 0, which would be how many roots? 4. Interesting yet again. So we have 0 and 1 plus or minus root 3. So that would be using quadratic formula. So all that stuff we learned last chapter, we're still going to be using it. It's one reason why last chapter is so important. All right, let's take a look at one more on this page. 4x cubed plus 7x squared minus 5x equals 6. All right, first step, we need to get it equal to 0. Before we can even start our factoring steps, let's get it equal to 0. So subtract 6. All right, now we can factor out what they have in common. Well, they don't all have an x. See, 4 is 2 and 2. 7 doesn't have a 2, so we're not going to be able to factor out any numbers. So we can move on to step 2. Let's look to see what, how many terms they have. 4 terms? Hey, let's try factoring by grouping. Well, if we factor out an x squared, we're going to end up with 4x plus 7. And we're not going to end up with 4x plus 7 over here. So factoring by grouping isn't going to work. Well, that's the end of our steps so far. Well, all that means is we have to do something else. And that something else is what we're going to see right now. And then we'll actually come back to this problem. We will finish this problem, but first, let's see what we have to do. Before we get to what we have to do, I want to get an actual graphic of the steps. So step 1, factor out what all terms have in common. Step 2, we're going to look at the number of terms. If there's 2 terms, we have to ask ourselves if it's a special factor. 3 terms, can it be factored like a quadratic? 4 terms, can you use factoring by grouping? If one of those was no, or if it had more than 4 terms, which is a possibility, we need to move on to step 3, which would be use the rational root theorem to help us factor it. And the rational root theorem is what we're going to learn next. So let's see what this rational root theorem is all about. What it says is, for a polynomial p of x, all rational roots can be written as p over q, where p is a factor of the constant and q is a factor of the leading coefficient. Makes perfect sense, right? Not really, but it will in just a minute. Now, generally speaking, like this will come up again in pre-calculus, it'll come up again in calculus, it'll come up again later this year. We get to something to factor and we can't do it, and so I ask people, how do we do it? And they say, I don't know. I'm like, use the rational root theorem. And they look at me with blank looks because they never remember what this is. And then I say, use the P's and the Q's, and that's when they usually say, oh, which by oh, I mean it's a swear word that I don't want to put on a video. So, but that's how people remember it. It's the P's and the Q's, because we have P's and Q's. So, let's look back at our polynomial. We have 4x cubed plus 7x squared minus 5x minus 6 equals 0. What the rational root theorem is saying is that all of the possible rational roots can be written as a factor of -6 divided by a factor of 4. So let's list out the factors of -6. Those are the p's. That would be 1, 2, 3, and 6. And it could be either positive or negative. And that doesn't matter that it's -6. Even if it's +6, it could be positive or negative. So we end up really with plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then the q's are going to be the factors of 4, which would be 1, 2, and 4. And you might be thinking, well, how come the q's don't have plus or minuses? We really don't need them, because we're going to go p divided by q. If the numerator has both signs already, we only need one sign for the denominator. So it doesn't really matter which one you use. You just have to remember to do all, like, both positives and negatives as options. So let's find our possible roots here. We're going to go p over q. So we can go p's over 1, which will just be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. We can go the p's over 2, which would be plus or minus 1/2, plus or minus 2/2, plus or minus 3/2, and plus or minus 6/2. But you can probably notice that 2/2 simplifies to 1. We already have 1. 6/2 simplifies to 3. We already have 3. I know. We'll get rid of those in just a second. But first, let's put the p's over the 4. And so we have plus or minus 1/4, plus or minus 2/4, plus or minus 3/4, plus or minus 6/4. And so these are all the possible roots, but we can narrow it down a little bit. 2/2 is 1. 6/2 is 3. 2/4 is 1/2. And 6/4 is 3/2. So we don't actually have to include those because we already have them. And so we can write them out. And now, it's just guess and check. You might be thinking, wait a second, we're doing all this for guess and check? How is this working for us? We still have 1, 2, 3, 4, 5, 6, 7, 8, plus the plus or minuses. So we have 16 possibilities. True. We narrowed it down to 16 possibilities from an infinite number of possibilities that we started with. So really, this is quite successful. The guess and check, the guessing will get easier with practice. I'd recommend starting with the 1s, 2s, and 3s, because if 6 was our root, that means that the rest of them would have to be 1, like 1/2 and 2, 1/4 and 4, which isn't even a possibility. And so the 1s, 2s, and 3s will most likely be in there. And also later on this week, I'm going to show you another technique that will make your guesses really, really good. But the process that we're going through is still going to be important. I'll show you why in just a second. So let's start with a number. Let's start with 1. And I am going to use guess and check. I'm wondering, is 1 a root? Synthetic division. What am I looking for? I'm looking for a remainder of 0. If I get a remainder of 0, yes, it's a root. It's a factor. If I don't, then no, it's not a factor. This is what we did last time. Synthetic division. Remember, I said it's going to be your warm, cuddly blanket. You're going to be doing it a lot. The better your guesses are, the less you'll do it. But you'll do it a lot, and it should be getting pretty quick at this point. So we can set up our coefficients. We can draw a line, and then we can do the synthetic division. We bring down a 4, multiply, add, multiply, add, multiply, add, and look at that. It's a root. So 1 is a root. And what we're left with is 4x squared, because we always drop 1, plus 11x plus 6. But we don't only have 4x squared plus 11x plus 6. We also have this factor when x equals 1. Well, if x equals 1, that means that x minus 1 equals 0. And so we have factored our polynomial to an extent. We have a quadratic now. We can deal with quadratics. Can we factor this one? I'm not sure. Well, I am sure we can. But even if we couldn't, we could use a quadratic formula at this point. But this one does factors into 4x plus 3 and x plus 2. If we check it, we get 4x squared plus 8x plus 3x is plus 11x plus 6. And x minus 1 equals 0. So now 4x plus 3 equals 0, x plus 2 equals 0, or x minus 1 equals 0. Which, if we subtract the 3, divide by 4, x equals negative 3/4, x equals negative 2, or x equals 1. And so that's the rational root theorem. It gives us our possible roots so that we don't have to guess just wildly. It'll give us some logical guesses to make. And it narrows it down, and you can use some common sense to help narrow it. And if you're going through this and you're getting crazy fractions, is there anything that's going to get rid of a crazy fraction? Probably not. So it's probably not going to be 0. If all of a sudden your numbers are getting really, really big, well, it still has to get back to 0. Is it going to get back to 0? Probably not. So you don't even need to necessarily finish it all the way to the end if it starts becoming unwieldy, because it's probably not going to get back to 0, and that's what you're looking for. It's either 0 or not 0. Let's do another one of these. Here's a fourth one. Oh, no. Oh, x cubed. Oh, 3 roots. It's weird. X to the 4th. Step 1, factor out what they have in common. Oh, they have nothing in common. Step 2, look at the number of terms. 5 terms, which means that we don't even have a possibility in step 2. Step 3, rational root theorem. Use the p's and the q's. Well, the q's is just 1. That makes it nice. The p's are 36, which is obnoxious because there's lots of factors of 36. In fact, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 12, plus or minus 18, and plus or minus 36. When doing this, I'd recommend starting out with your low ones, because people tend to remember, okay, so 1, 2, 3, 6. All right, well, let's see. 6 times 6 is 36, so that's going to be the flipping point. All right, so then we go backwards. 3 times what is 36? 12. 2 times what is 36? 18. And 1 times what is 36? 36. With 36s, 18 is forgotten a lot. Chances are it's not going to be the 1, but just in case, it's important to be there. And being that q is just 1, then these are the possible roots. So we don't even need to worry about that. So start with 1. Seems a good place to start. We get our coefficients. We don't have to worry about any zeros in there. Draw a line, and then we can do our synthetic division. Bring it down, multiply, bring it down, multiply, bring it down, multiply, bring it down, multiply, and it equals not 0. I really don't care what it does equal, because it's either 0 or not 0. All right, we'll try something else. We could try negative 1. I'm going to try 2. Notice we start with the same 1, 2, negative 11, negative 12, 36. Draw the line, and do the synthetic division. Bring it down, multiply, bring it down, multiply, bring it down, multiply. Hey, it's 0, which means we found a factor. It also means that we only need to worry about this piece now. We started out with x to the 4th. We now have x cubed. possible you'd be able to factor by grouping here. Not necessarily horribly likely, being that you're already in this process. I'd stick with this way. We need to get it down to x squared. Let's see, x to the fourth took it to x cubed. If we find one more, we'll take it to x squared. To find the number of factors you have to find by this way before you can deal with quadratic, just take your degree, subtract 2. 4 minus 2 is 2. We just need to find 2 factors. 2 is one of them. Let's find another one. Now we're going to start with the 1, 4, negative 3, negative 18, because that's going to help us take it down. If we went back up to the original equation and we found another factor, great. We have another cubic. We don't want another cubic. Another nice thing about starting here is that my constant is no longer 36. It's 18. If I look up at my possible numbers, see, 1 still works, 2 still works, 3 still works, 6 still works. 12 is not a factor of 18, and neither is 36. So I don't need to use those. So we have those. You can try a different number. When you find one, I'd recommend trying the same number a second time, just in case it happens to be a double root. I mean, you'd feel pretty silly if it was like x plus 2 times x plus 2 times x plus 2 times x plus 2, and you found 2 once, and then you moved on, you tried all the rest of them. Just try 2 again. So we're using 2, and notice I'm using these numbers. So draw the line. We can do our synthetic division. Bring it down, multiply, bring it down, multiply, and we got 0 again, which means that 2 is a root once again. So here notice we have a double root. We have 2 twice. Notice also we have a quadratic, x squared plus 6x plus 9. And so we have our x minus 2. Then we have another x minus 2 from this one. Then we have what's left. It's important to keep these factors because when we solve, we need all those factors. Now let's see, x squared plus 6x plus 9. That looks like something we could probably factor. In fact, x plus 3 times x plus 3. And so we have x minus 2 times x minus 2 times x plus 3 times x plus 3 equals 0, which means x plus 2 could equal 0, or x plus 3 could equal 0. If x minus 2 equals 0, means x equals 2. If x plus 3 equals 0, that means that x equals negative 3. And both of these have a multiplicity of 2. So that is another example of the rational root theorem. Again, it's just gives us the roots, allowing us to guess and check and find our possible roots. And then multiplicity 2. We have another theorem called the irrational root theorem. And we're going to go through this one pretty quick. This is nowhere near as important as the rational root theorem in most things. And what it says is if you have one root that has a conjugate that's irrational with a conjugate, it means that its conjugate will also be irrational. Just like we had with quadratics. If root 3 is a root, it means negative root 3 is a root as well. Generally speaking, we don't need to worry about it too much, because how do we get the irrational numbers? We get it from the quadratic formula, which has a plus or minus built in. We get it from having x squared equals a number. We square root, plus or minus the square root of something. And so we get that all the time. But let's see how that can happen in our factoring. Sorry about that. So this is a problem that we already actually did. 4x to the fourth minus 2x cubed minus 2x squared. We did this one. We factor out the x squared, and we saw, hey, it's a quadratic formula, and so we plugged it in. And again, we did this one. I actually just copied and pasted the whole thing. And we got x equals 1 plus or minus root 3, or 0. Notice we get the conjugate right there. It happens naturally. Another way we could get it is from grouping. Hey, we have x squared here. We have a negative 2 here. So we can pull those out, get x plus 1. You can now pull the x plus 1s out. X plus 1 times x squared minus 2 equals 0, which means x plus 1 equals 0, or x squared minus 2 equals 0. So x could equal negative 1, or x squared could equal 2. X could equal plus or minus root 2. And so it can happen there as well. And then you might be thinking, well, so here we always have one root that is rational, and then the other two are irrational. Is it possible to have all roots being irrational? And if so, how could we even find it? Because the rational root theorem won't help you. The answer is yes, it is possible, and yeah, you can find them. If we have something like this, x to the fourth minus 10x squared plus 21 equals 0, well, they don't have anything in common, so let's see, count the terms. We have 3 terms. How can we factor something with 3 terms? Is it like a quadratic? Well, it's x squared and 4, so yeah. Let's see, what times what equals 21, but it has to give us negative 10. If you're thinking negative 7, negative 3, it's a good thinking. And so we get x squared minus 3, x squared minus 7 equals 0, which means that, and neither of these two will factor, so x squared minus 3 equals 0, x squared minus 7 equals 0, which means x squared could equal 3, or x squared could equal 7, which means x equals plus or minus root 3, and plus or minus root 7. All right, well, those happen really naturally. So how is it that might, how would we have to actually use the irrational root theorem? Well, if I tell you to write a polynomial with the following roots, negative 3 and root 2, you have to know that, well, if we have root 2, we also have to have negative root 2. And so, well, if negative root 3 or negative 3 is a root, that means the factor that gives us that is x plus 3. Root 2 is a root, which means we have x minus root 2. And we also have to have negative root 2, so we also have to have x plus root 2 equals 0. You could leave it like that. Some people really feel the need to multiply these two things together, which is pretty easy. It's difference of squares. You can go ahead and do that to get x plus 3 times x squared minus 2 equals 0. You don't have to multiply it all the way out, though, especially if you have like 5, 7 things multiplied together. Just leave them as factors. That's fine. So this is how you would really actually have to use the irrational root theorem, because when you're solving, the plus or minus happens automatically, and it's not really something you need to worry about. So we haven't had any of these yet, so I'm going to give you a couple to try. This is the last thing that we're doing here. Just 2 problems. See if you can do them. We have x cubed plus 3x squared minus 9x equals 27. And x to the fourth minus 3x squared minus 4 equals 0. So go ahead and pause this and see if you can factor and solve. And then when you think you're ready, come on back. All right, how do you think you did? Did you get 3 roots over here? Well, maybe. How about over here? Did you get 4 roots? You might be thinking, yeah, I did get 4 roots. If you got 4 roots, you might actually be a little bit ahead of things. And we'll see that, though, in a second. So, first step here, get it equal to 0. And then, factors. Can we factor anything out? No. There's 4 terms. Can we factor by grouping? Hey, it looks like we can factor by grouping, which is nice. Anything to keep us from using the rational root theorem is always good. So let's see, x squared, negative 9. So we get x plus 3's. We can factor those out. X plus 3 times x squared minus 9 equals 0. X squared minus 9 is a difference of squares, so we could factor that. I apparently didn't factor that. We could have factored that. If you didn't, it still works. You just get your plus or minuses. As opposed to x plus 3 times x plus 3 times x minus 3. It's the same thing. but x squared minus 9, so x squared equals 9, x equals plus or minus 3, so x equals 3, or plus or minus 3, so it really just equals positive or negative 3. Positive 3 is a double root. It has a multiplicity of 2. That's what double root means. Triple root would have a multiplicity of 3. I didn't specifically ask for that, so you don't need to tell me, but it's just good to be aware of that. That will affect how it graphs and stuff like that. How about over here? Well, they don't have anything common, but 3 terms we can factor like a quadratic. X squared minus 4, x squared plus 1. X squared minus 4 will factor. X plus 2x minus 2. X squared plus 1 does not factor. It is not a difference of squares. When it's something squared plus something, that will not factor. And when we think about it, we're trying to get it equal to 0. Well, if one thing we know about x squared is it's going to be positive, or 0, when we add 1 to it, it's going to be positive, and positive things don't equal 0. But x plus 2 could equal 0. X minus 2 could equal 0. This one's not. We'll see that in a second. So x equals negative 2, x equals positive 2, x squared equals negative 1. And you're thinking, well, but this works. We square root. X is going to equal plus or minus I. Yes, but not yet. Hold your horses. That'll be coming in a later section. Right now, it's just not real. Don't need to worry about it. So our 2 roots are 2 and negative 2. And if we're thinking, well, there should be something there. To check these, you can always graph them. If we graph this one, we have, remember, our roots are where they hit the x-axis at negative 2 and positive 2. That imaginary deal is happening right in this area. See how it's just like there's something there, but it doesn't quite get up to the line? That's what imaginary roots do to us. But we have a root at negative 2 and positive 2, and that's it. So, how did you do on those? Yeah. So that is the end. I don't have a timer on this, but it probably went longer than I was hoping. But it usually goes bell to bell in a full class period, so it's a rough one. Anyway, make sure you comment. If you feel like it, you could tell me what happens to that other number. You know, we have a pair of numbers inside of a square root. One makes it the outside. What happens to the other one? But comment, and be ready for a group activity on Monday. I'll see you then.